my name is Jenna Zeigen, and today I'll be talking to you about the browser and the brain. In case you want to tweet at me, questions, comments, concerns, I'm Zeigen Vector on Twitter, and you can also find these slides at that URL. I came here from Brooklyn, and I'm the organizer of two events that happen in the New York City area. One is NationJS, which is a pretty popular monthly JavaScript meetup in Brooklyn, and I also organize EmpireConf, which is a yearly all things JavaScript conference that happens in Manhattan. All right, so what's this talk going to be about? So I'm going to be comparing bits of how human cognition works and how the human brain works to how the browser works. So I'll be talking about three overarching concepts. One is understanding, so how do humans process language and how does the browser process HTML, CSS, and JavaScript. Visualizing, so how does the human visual system work versus how does the browser end up putting pixels on your screen. And task management, can humans multitask and can browsers multitask? Yeah, let's kick this off. But first, I want to make an overall caveat that humans make computers, so humans know how computers work. But humans don't really know all of the ways that humans work. And we do science to try and find out these answers, but science isn't always perfect. We still don't have answers to even some of the things like I'm going to talk about. Like we don't know if they're 100% true. Yeah, so that's cognitive science and neuroscience for you. All right, so let's start with understanding. So how does the browser process HTML, CSS, and JavaScript, and how does the human mind process natural languages? So most programming languages have a vocabulary described using regular expressions and a syntax that is described by a context-free grammar. And what a context-free grammar is that means that there is a set of production rules that can describe all the possible strings in a language. So in context-free grammars, these production rules are simple drop-in replacements that can be applied regardless of context. And so that means that you can keep replacing bits of the string with other bits of the string infinitely forever. I wouldn't recommend creating something that long, though. Probably wouldn't send very well over the internet. Programming languages are generally well-defined in a spec. I'll also be talking a bit about parsers, so I'll go over what a parser is in general. So a parser's job is to take a document and break it into a structure that the code can use based on the syntax rules the document obeys, so either the language itself or the format that the document was written in. And the result of parsing is usually a tree of nodes that represent the structure of the document. And this structure ends up being a parse tree or a syntax tree. And parsing can generally be separated into two parts, lexical analysis and syntactic analysis. So lexical analysis is the process of breaking down the input into tokens, which are the language vocabulary, the collection of valid building blocks. And this is done by what's called a lexer or a tokenizer. So if we were to have a language that just modeled addition, so if you had like 2 plus 2, the 2, the plus sign, and the 2 would all be tokens in that language. Then we have syntactic analysis, which is the process by which the language syntax rules are applied. So what tokens can go next to what other tokens and in what order, and this is done by an actual parser. So you know, in the addition language, you need to have like the number and then the plus sign and then the number and then on and on in that rule, and you can in that order, and you can just like drop in number plus number for another number. That would be the replacements. So curveball, HTML is not a context-free language, and therefore cannot be parsed by a regular, as in regular expressions, parser. And this is because the spec says that it's not context-free, because it's supposed to be fault-tolerant. HTML is supposed to be really forgiving of human error. It does have a well-specified spec, though. So browsers have to write custom parsers for HTML that are like a bajillion lines of C, but at least it makes it easier for our mushy human brains to write and mess up, and we'll never get an HTML syntax error. Lucky for us, CSS is a context-free language and is therefore easier to parse. And what this means is that we can actually generate parsers for it by feeding software rules of the language. And this is easier than handwriting a parser that obeys all of these rules. So WebKit happens to use two well-known parser generators, Flex for creating the lexer and Bison for creating a parser. And Flex's input is a file that contains the regular expression definitions of the tokens, and Bison's input is the language syntax rules in what's called a Bacchus normal form. So both HTML and CSS parsers end up creating a tree that represents the language it parsed, so the DOM and CSS trees respectively. And we'll talk about what ends up happening to these in a bit. JavaScript is also more or less context-free and can use a regular parser, but browsers these days end up complicating things in order to optimize the execution of the JavaScript. So I happen to know a bunch about V8 just because they're putting such great content on the internet in talks and blog posts, so I'll talk about generally what this looks like in Chrome and other like V8 environments. So I happen to know that V8 uses two parsers, an eager parser and a lazy parser, to eventually create an AST, an abstract syntax tree, and a structure that represents the scope. An eager parser is the full parser like what I just explained. So it parses all of the functions for compilation and builds the AST and the scope structures and finds all syntax errors and will like yell at you if you ended up writing something with a syntax error. So it is not fault tolerant. The lazy parser is also called a pre-parser, and it skips over functions that shouldn't be compiled yet. It doesn't build an AST, but does build a scope structure, but doesn't process that fully, and it finds only a limited set of errors. So then the AST and the scope structure are going to get turned into low-level code. So in the case of V8, the bytecode generator is going to walk the AST and scope structures and turn it into bytecode. But this step, it could be done by any what's called a baseline compiler. So in the past, V8 using full code gen would return machine code. Then the next step for V8 is that the bytecode gets executed by an interpreter, which is called ignition. The bytecode is also then fed to an optimizing compiler, which recompiles the functions that get used a lot and are worth speeding up. In V8, there's only one optimizing compiler called turbofan. And because JavaScript has a just-in-time compiler, or JIT compiler, the code is being compiled at runtime, and then the information from execution is used from initial runs is then fed back into the compiler and is used to speed up the function, assuming it's going to continue handling cases similar to what it's already seen. So if you start off and you keep feeding this function a certain type of object or like a number, the optimizing compiler is going to start to optimize the compilation of that function to make processing numbers super fast. But then if all of a sudden you pass the string, it's going to have to go back and use the de-optimized version, and then you're not going to be taking advantage of all of the great things that the optimizing compiler does. All right, human languages can happen a little differently. Human languages, though, also do have a lexicon or a vocabulary of valid words that can be arranged in a certain way based on a set of syntax rules, just like programming languages. But the syntax for human languages it's not context-free, and the lexicon cannot be described by a regular expression. So we're a little more wild, wild west in our more naturally evolved natural languages. And there's also no spec for natural languages like there is for programming languages. Human language also contains a ton of ambiguity. Sorry for that typo. And human language is more ambiguous than you'd think. And this is because we're really good at finding the intended meaning of a word or sentence based on context and frequency. This also, as you know, I did my honors undergrad thesis on puns, so I happen to know a bunch about ambiguity because the fact that human language is ambiguous makes some types of puns possible. So, there's a lot of words in English that have multiple meanings, and we're generally able to figure out what the intended meaning of the word was, based on the context that the word appears in, and also how often those meanings occur compared to other meanings within the language. So what we do know is first, the human brain has to parse a pretty fluent speech stream into words. So when someone is talking, there's no actual boundaries between words. Generally, if they're talking and if they're not really paying attention to making sure that there are word boundaries, so the brain has to then come in and chunk it up based on what we already know about the language. We also can't, our brains aren't capable of perceiving all of the sounds that are being made, and even in perfect conditions. And then also, in general, there's going to be ambient noise, coughs, so you might not hear everything, even if you could. So what our brains are receiving is only a sketch of the meaning, but we tend to use top-down information about what we know about the language to fill in the gaps, and we don't even notice that we're missing parts of the sound. So our minds are going to match the sounds to words in our mental vocabulary, in our mental lexicon, for probable matches. While we only have theories about how this works, the leading one suggests that the sounds activate several potential matches in parallel, and as the context progresses, one winner eventually emerges. So this whole process is kind of like how the human lexer works. Once we have access to a word, we then have access to both its meaning and its syntactic and thematic roles. So what role it can play in a sentence, whether it can be a subject or an object, or verb, adverb, etc. So then we can go through and parse the sentence. And we're not 100% sure, specifically with this, how this works. But we do know that what can happen is we're going to parse the sentence and compute a syntactic structure, just like what we discussed with programming languages. So first we're going to determine the syntactic category of each word, and then combine those categories to form phrases. And at this point, we're going to start to construct the representation of the meaning of the sentence. And again, how exactly we arrive at this correct meaning is still a pretty open question in psycholinguistics, in the study of how we process and comprehend language. So there's two conflicting theories with pretty solid evidence supporting both. One of them is the modular view, that the phases involved in this process occur separately and in different modules. So a pretty popular version of this is called the garden path theory, and it says that we construct the simplest parsed first based on the syntactic information, and then in the second round, the semantic information is used to determine if that parse makes sense based on context. And if not, you have to go back and reparse. And this explains why we fall for sentences such as, the horse raced past the barn fell. And these are called garden path sentences because you're led down this beautiful garden path until the end when you realize you did it wrong. So another view of this is called the interactive view. So in this view, all available information can be used at once in parsing the sentence. So you're going to have the syntactic, semantic, and contextual information all there for you from the beginning. So the semantics of the sentence can come in and play an earlier role in determining if the parse is plausible while the parse is unfolding. So you get just-in-time parse validation from semantic information. Also, we don't know if this happens in serial or in parallel. So in a serial account, only one interpretation is constructed at a time, and then another is only constructed if the first turns out to be wrong. In parallel models, all the interpretations are constructed and then looped through in order of plausibility until one that fits is entertained. Also, humans are forgiving of syntax errors, and also apparently of spelling errors, because I looked through those slides so many times to try and find this, if there were any spelling errors, and I couldn't see it. So thank you, top-down processing, for allowing me to have a typo in my slides. So I know you're all programmers, so we probably want to have some fact that we kind of know to be true. So we do have a better sense of the neuropsychology of language processing, so we know where this is all occurring in the brain. And it occurs in an area called Wernicke's area on the dominant hemisphere of the brain, which for 97% of people is the left hemisphere. All right, moving on to visualizing. So we're going to answer the question, how does the human visual system paint a picture of our world, and how does the browser render pixels to the screen? So we'll switch it up and we'll talk about humans first. So the first thing that's going to happen is visible light is going to be reflected off of objects in the environment and reflected onto our retina with the help of the cornea and the lens and other clear things within our eyes. And then the image is going to end up getting projected onto the retina upside down and backwards. Then the retina is, photoreceptors in the retina are going to transduce the electromagnetic energy into neural signals using cells called rods and cones. Rods are primarily found in the periphery of your retina and are used to see at low levels of light, and they have a relatively slow temporal resolution, so flickers above 15 hertz aren't detectable by them, or they have what's called a flicker fusion threshold of 15 hertz. Cones are primarily found in the center, or what's called the fovea of the retina. And there are 3 types of cones that differ in the wavelengths of light that they absorb. One type is a short type, which likes blue light. Another is the middle type, which likes green light. And then another is the long type, which likes red light. Cones are primarily used to distinguish color and other features of the visual world at normal levels of light. And they have a high temporal resolution, so flickers above 60 hertz aren't detectable by them. So that is 60 frames per second. Sound familiar. Step 3, these signals are going to get sent via the optic nerve to the brain, where they meet at a structure called the optic chiasm, where the signals are combined and split by the visual field and sent to the opposite side of the brain. So, like, each eye that we have, it's not like your right eye only sees, like, just the right side of the world. There's a bunch of overlap in the middle, so at this structure, just information from the left side is going to get sent to the right hemisphere of your brain, and vice versa. So then these signals are going to get sent to the lateral nucleus, so there's one on each side of your brain. And this information is going to get collated within each LGN. Each LGN has 6 layers, and each, cool enough, preserves the topography of the retina with corresponding parts on top of each other across all of the layers. So layers 1 and 2 get information from the rods about movement and depth, and layers 3 to 6 get information from the red and green cones about colors and form, and the blue cone information just gets sent from in between the layers. Then the signals end up at the primary visual cortex in the occipital lobe, or in region V1. And just like in the LGN, there's a correspondence between the location in V1 and the part of the retina. However, there isn't a straight mapping of retinal area to brain because we have a fovea, which needs more representation within V1, and this is called cortical magnification. So thus it's said that the retina, just like the LGNs, have a retinotopic map of the opposite side of the brain's visual field. And there's some cells in here that are going to fire a lot for a very specific angle of a contour or edge. And then others are going to respond even better when that's moving through the visual field that they're responsible for. And then other cortical cells are going to respond to color. Then finally, the signals get sent to higher visual processing centers that help us actually perceive what we are seeing. All right, now we'll talk about computers, because that's why you're here. Step 1, again, so we talked about in the language section that they're going to end up with these DOM trees and CSS DOM trees. So now it's time to turn language into pixels. So step 2 of this process, these trees are going to get combined to form a render tree. And so this tree is going to get made by traversing the DOM tree, and for each visible node, applying rules from the CSS DOM tree, and adding that to a new tree called the render tree. And the nodes that aren't visible, for example, are script tags, those with display none, etc. Then the browser is going to traverse the render tree, calculating the location of all of the size, and location and size of all of the elements within the device's viewport. So in this phase, all relative measurements are converted to exact pixel locations on the screen. So we're starting to create that map of what's going to go on the screen. Then the browser is going to traverse the render tree, creating layers of bitmaps from the bottom up in 12 phases. So at this point, we're going to determine what color to paint pixel and where, again, creating a layer, a bitmap, so like a little picture for each layer. And then these pictures are going to get sent from the CPU to the GPU, where they're smushed together into one picture, which then the browser can use to put pixels on your computer screen. And then we're going to do it again, maybe, and optimally this is going to be 60 times a second, or every 16.66 milliseconds, which happens to be the Flickr fusion plateau for cones. I do not think that's a coincidence. All right, task management. So can the human mind multitask, and can the browser? This is going to be a little shorter, but I think cool to kind of get into. So human attention, there's a bunch of metaphors that's often used for it. So attention as filter, so we're going to filter out the stuff we don't want to be paying attention to. Attention as spotlight, we're only going to focus on the stuff that we do want to be paying attention to. And then something a little more cognitive science-y, attention as control. So what control means is that we're going to block out unwanted distractions and automatic processes. So an example of how control works is, so this might look familiar to you if you had an email account in the early 90s. But this is actual science. It's called the Stroop task. If you're not familiar with it, the idea here is you're supposed to say the color that the word is written in and not the word itself. And this is pretty difficult, even if you have normal color vision. And it's funny because this is easy if you have normal color vision. This is easy, but this is hard. And the reason here is because like reading is an automatic process, so we have to dedicate attention to like pushing down our like automatic instinct to read the word, and that like attention that we're paying to it is going to take away the resources that we have to do the task at hand, which is say the color of the pixels in this case. But none of these really have to like, I can't really figure out a way that this is going to work to talk about anything in computers. But my like programming brain started thinking about attention as threads, and then there's something to talk about. But we have threads in computers so that the computer can do more than one thing at once. But humans are pretty bad at multitasking. So there's a bunch of studies like unintentional blindness. So there's a video I remember watching in school where the idea is you're watching this video and there's like two teams passing the ball back and forth, and your task is to count the number of times only one of the team catches the ball. And I'm not going to spoil it for you in case you want to like go back home tonight and try and find this video. But like you miss something pretty big because you're paying attention to something else. There's also other experiments that scientists use to figure out how bad we are at paying attention to things. One of them is called a dichotic listening task with shadowing. So in one of these experiments, you're going to have like two speech streams, one going in one ear and one going in the other ear. And the idea is that the scientists are going to ask participants to repeat back only one of the speech streams. So in this case, like we don't remember anything that's going on in the ear that we're not supposed to be like repeating back. We also don't notice syntax errors. And so like we're pretty bad at registering anything we're not paying attention to. So we like really can't do two things at once. But what about the browser, right? So like I think there's one thing that we know, which is like JavaScript doesn't multitask. It's single-threaded, non-blocking, and asynchronous. And it has this event loop that was made so that the browser could do more than one thing at once. But JavaScript itself, one capacity being JavaScript. But as I mentioned, and as we learned about earlier, about all the cool things that a browser can do, there's all these cool APIs that JavaScript can call out to within the browser. So we have like the DOM APIs, other browser APIs, C, web workers, making the browser itself effectively able to multitask. So there's one thing we learned. I hope it's that browsers and brains do not really work the same, but there are perhaps some things that browsers do in order to help our brains be human. So if you're interested in learning more, this is all the stuff I read to stand here and talk to you for 25 minutes. I didn't read all of the books, but I like citing my resources because I'm a good scientist. So thanks for listening. Feel free to tweet at me, look at the slides again, or find me afterwards.